In chapter 3, we cover node voltage analysis. And the important concept here is that where we have been exploiting resistances in series and parallel before to reduce the complexity, exploiting the fact that we can distribute currents and voltage using our division principles appropriately to help resolve those various voltages and currents at all the different resistances is nice, but it's not possible sometimes for some circuits to have those combinations. So as you see here at the top of page 47, we want to know how can we approach finding voltages and currents at different circuit elements when they're not in series and parallel. So the technique we're going to use is called node voltage analysis, or NVA. And the important phrase there is node voltage. So we're going to be looking at voltages specifically at particular nodes or areas within the circuit associated with the conductors, okay? So, and the nice thing about NVA is that you can apply this technique to any circuit. Again, it's not depending upon series or parallelism at all. And so we're going to start with this figure 12 circuit, circuit number 12 here. And if you look very carefully here, you can see, for example, that resistance 2 and 3, they're not in series because of 4, resistance 4, and you can see 4 and 5 are not in parallel because of resistance 3. And so this is a classic example of a topology in which there is no series or parallelism, right? So the idea here is to represent voltages at different regions, or in this case, nodes of the circuit, which has already been marked here for you. This is going to represent node 1, this particular connection here. The connection between these three resistances will be represented as node 2, and the one over here would be node 3. So let's go ahead and write that just so that we're understanding what we mean by nodes. So that's node 3. This right here is node 2. And this right here is node 1. And what we're interested in is representing the voltages at those particular nodes, all right? Now, we already know that we can represent voltages, for all the circuit elements. And of course, we have this particular voltage source here, and we have voltages that go across each of these circuit elements. And let's just represent, for example, the voltage across R2 using a voltage arrow here. Let's call this voltage V sub Y, plus minus polarity. So that this means if you're coming through this direction, you would have a negative voltage. If you're going back to the right, you're coming into the positive pole, and that would be positive. So it'd be PRC going this direction. Similarly, let's do that for R3. Let's represent a voltage arrow here. This is pointing to plus, minus, and let's call this V sub X, okay, that voltage X. Again, if you're traveling from left to right, it'll be a positive voltage. If it's negative, if it's from right back to left, you're coming into the negative pole, and that'd be negative, right? And then we can do the same thing up here. Let's just say arbitrarily, let's represent the voltage polarities for VZ, and this is plus and this is minus, okay? Right? So the idea here with node voltage is we're interested in the voltage at V1, V2, V3 relative to a reference node. And the reference node is always marked by a ground. So in this case, the reference node is this bottom node, okay, of the circuit. And this is the way you would designate a ground. And it's important to do that. So we'll represent these nodal voltages relevant to that reference, okay? As indicated here in the text, the reference polarity is defined to be positive at node 1 and negative at the reference. So if we were drawing a voltage arrow representing node 1 voltage, then we would represent a voltage arrow like this, call it V1 minus plus that way. So you're negative down here at the reference node, but positive at the node itself, right? And similarly, we will do that for the other node voltages. Again, drawing a voltage arrow from the reference node minus plus there, okay? So you're positive at that node, negative at the reference node, okay? And we'll do one more here. Okay, so we're drawing it with regard, with reference to the direction here. from the reference node to the node. So it's from the reference node to the node voltage. But if we're thinking about looking at traversing loops, if you come into the positive here, so you're coming into the node here, it's positive. If you're coming from the reference node up through the circuit, in this case, up through this resistance, it would be negative, okay? All right, so using these voltages, we can derive voltages and currents for all the circuit elements, right? So what we'll do is we'll use our Kirchhoff rules as we can with these node voltages and be able to determine our goal, let's say, is to determine Vx, Vy, and Vz. So in other words, we want to use the node voltages to determine what the voltages are through those resistances. Because remember, we cannot get an equivalent resistance. They're not in series or parallel, okay? So we're gonna have to use, if we can figure out what the voltages are at these nodes, then we can use them to determine what the voltage is across each of those circuit elements, right? So, and then we'll use Ohm's laws appropriately to get the currents and so forth. So if we start off by looking at KVL, right? So what we're gonna look at is at this circuit, if we were looking at KVL, all right? And more specifically, suppose we are traveling around the lower right loop in a clockwise fashion. So in this case, we are looking at the lower right loop down here, okay? So I'll use a change of color here. So if we were looking at KVL and we're doing clockwise on the lower left. So here's KVL, and we're looking at a representation of the sum of all the voltages and setting it equal to 0, okay? So the way that happens with node voltages, all right, is we traverse the node voltages, we're coming into the negative polarity in a clockwise way. So we would represent minus V2. And then we will come into the positive pole representation for the circuit element, which in this case is a resistance. So that'll be a plus Vx. And then we're coming into the node voltage here, again, at the positive polarity for V3. And so this is why the equation for KVL is indicated here is minus V2 plus Vx plus V3 equals 0. We're going to get a lot of experience with a couple examples of making sure we have the right signs for these voltage polarities. So if we solve for Vx, what we determined is, interesting enough, the voltage across this resistance here is the difference between V2 minus V3, okay? Which if you think about it, that kind of makes sense because voltage is measured across, right? So whatever the voltage is here and the voltage is here, the difference between those two is the voltage across that circuit element, right? Okay, so, and again, Vx is the resistance, is the voltage for resistance 3. Now let's derive similar formulas for Vy and Vx. So we will then use different KVL loops for those circuits, okay? So, so that I'll write it here so we can keep seeing that circuit diagram here. If we did KVL here, and let's say we were looking for a relationship for Vy, then we probably would want to use, again, Vy is right here. Why don't we use the lower left loop here? So let's say lower left clockwise. So that will be our KVL loop this time, okay? So again, we're gonna traverse the voltages that we encounter in that lower closed path there, okay? So if we do that, then we can see that we're coming into the negative polarity for voltage 1, which is minus V1, okay? And we'll talk about what that means relative to the voltage source in just a second, because you can probably see immediately we know something about the voltage here connected directly to that voltage source. But for now, we'll just say minus V1. And then we'll come into the negative pole for the representation for the voltage across R2, and that's minus Vy. And then we come into the positive polarity for that node voltage, so we'll get plus V2 equals 0, or solving for Vy, what does that tell us? That the voltage across that resistance is the difference between the node voltages 2 and 1. which kind of makes sense, okay? All right, again, it's the difference between those two. And then finally, if we push up just a little bit here and did a KVL loop for the upper loop, and let's say we went clockwise again, what node voltages would we encounter? Again, we're trying to get a representation for VZ. And so from the upper going clockwise, if we're going clockwise, let's say we would come into the positive pole for VY, right? Then we'd be coming into the negative polarity for VZ, so we get minus VZ, okay? And then we would come back into Vx here, coming across this loop, and it would be the negative polarity. So we have a minus Vx, okay? Set that equal to 0. What does that say? Solving for the voltage at Vz is basically, it's the difference between, the voltage Vy minus Vx, okay? So what does that tell us? We can use node voltages to get the voltages Vx and Vy, therefore we should be able to get it for Vz with KVL. So that kind of makes sense, right? So if we can get these two voltages, we should get the voltage there easily, okay? All right. So what we're going to do now is find a strategy to determine currents, and start with node 2, all right? So we're going to flip over to page 48. Okay, it's a good idea to keep that diagram in mind there, and if you need to flip back, we can do that. But one thing that I wanted to point out that we, I was hinting at earlier, is that if you go back to node 1, it's directly connected to this voltage source. What that allows us to do is to say immediately the voltage there is the same. So we notice that immediately V1 is equal to that voltage source, okay, right? If you're direct connected that way, right? So what I'm gonna do is a little sketch here of just sort of what node 2 looks like, because all we care about are the currents relative to it. So part of the diagram, this was V2, and we had this resistance, and we had a resistance coming out here, and we had a resistance here, okay? So I'm just sketching part of that previous circuit diagram. This was R2, resistance 2, this was 3, this was 4. Again, 2 and 3 are not in series, and 4 and the other one were not in parallel because of R3, for example. So we represented the voltages across Vy plus minus here, and the voltages this direction plus minus Vx here, okay? Right? And now we have a node voltage here, and we call this V2 plus minus, right? Okay, so we're after currents now. So if we notice at node 2, the current leaving through R4 so in other words, going down towards that reference node, okay? It's a 4, sorry. All right, is via Ohm's law, just the node, that voltage 2 divided V2 divided by R4, okay? So it's towards the reference node and away from node 2. Okay. So another way to think about it is that one way to look at it is that the voltage here at this node we represent by V2. The voltage at the reference node is 0, okay? It's grounded, there's no voltage. So you could think of that as like V2 minus 0 over R4. So what we discovered in the previous page is that the voltage across these circuit elements is the differences between the node voltages. But the voltage at the ground is 0, okay? So whatever the voltage is here, all right, we're doing V2 minus, starting there, V2 minus the voltage at the ground, which is 0. Again, divided by, according to Ohm's law, that resistance R4. So that's that current, okay? and the current flowing, let's keep going with this idea, the current flowing, let's say out of node 2 through R3 going to the right is, well, again, we have if we already have this node voltage here, right? Then if in this case we know directly that in this case we should have, if we have that voltage, it should be Vx divided by R3. If we know that that's the voltage across that resistance, then we already know by Ohm's law, then that has to be the current, Vx divided by R3. Okay, that's just what we used to do before, right? But the reason why this is useful now is this is assuming you know what Vx is. But remember, how would we ever find it if we don't have equivalents in series and parallel? Node voltages. On the previous page, we determined that, remember, or we just say we now know that we can represent Vx as the difference of these node voltages, V2 minus V3, okay? Again, this is previous page. So therefore, the current flowing out of node 2 through the R3 resistance is V2 minus V3 divided by R3, okay? And the idea here is this is an expression in node voltages. So again, we are determining the voltage across the circuit element using these node voltages, right? That's the idea. And so the generalization which follows is indicated by this simple strategy, okay? The idea is to find the current going out of a particular node in your circuit, okay, through a resistance, all right, toward some other node, K, and which could be the ground, okay? But you're flowing out of your node, your designated node, towards some other node. You take, this is the difference. You take the voltage you're at, and from it subtract the voltage where you're headed. So that makes sure you get the right signs, okay? And then divide it through the resistance you go through, okay? So back up here, that's exactly what happened, okay? Turns out over here in this diagram, we have node voltage 2, 3 on the right, 1 on the left. And so if you wanted the voltage across R3, you start it to node 2, you end up at node 3 and pass through that resistance. So it's V2 minus V3 divided by R3, okay? Similarly, if you wanted Vy, you could get it by V2 minus V1 divided by R2, okay? It's always, where are you at? Where do you end up? So it's always starting where you are, then subtracting the voltage where you would end up. And then what resistance did you pass through, okay? Keep in mind, this general for current is not needed when the resistance is corrected to node E and the ground, all right? In that case, this will be just 0. That's all that's going to happen. You would have Vn minus 0 divided by that resistance when you're going to ground, okay? So let's apply KCL at nodes 2 and 3 in that circuit and find all the expressions for the current, okay? So again, using this little diagram up here, that'll sort of help us. Node 2, KCL, what will we have? We're representing currents at node 2, okay, using the strategy above. So you've got 3 components because you have 3 currents coming out of that node, right? So one of them would be through R2, and you would start at V2 to minus V1 over R2. That's using our generalization. That's one of the currents. Then you have the current that leaves from the node and goes right to ground, all right? That's just simply V2 minus 0, or simply V2 divided by that resistance. And then you have the current V2 to V3 divided by R3, okay? And you have an equation. And so what we're going to end up doing is getting equations of node voltages, and then being able to solve those equations will tell us all the voltages that we need through any circuit element, okay? So, so one thing to note here is what we're doing is we're summing outgoing currents, okay? That will help you in terms of the strategy here is always representing outgoing, starting at your node and going outward, okay? And summing them to 0. Node 3, KCL. Well, at node 3, we would, you have to be a little careful here. I don't have the full diagram here, so you have to think about what, you know, what you've got 3 possible resistances, I mean, 3 possible currents to represent here, okay? So maybe the thing to do is to indicate back on this diagram is we really do have a resistance over here, R1 up here, and this has to come through it and come back down, right? So that's R1, okay? And then of course, there's another resistance here that we have to go through to get to the ground, right? And that was called R5. So we just need to make sure we know all the resistance that are involved, okay? So now we have enough information to do the sum of the outgoing currents here. Well, let's just think of it. There's no magic here how you want to do it. We could say, well, suppose you went through, started V through V3 and went to V2, you would pass through R3. So you'll have V3 minus V2 divided by R3 is what that current, outgoing current. You also have an outgoing current from that node to the ground. That'd be basically V3 minus 0, or just V3 divided through that by that resistance, sorry. And finally, and the reason I had to make sure we had to go back to the original circuit, because you will leave our node 3, pass through R1 to get to the node voltage at V1. So in that case, the last outgoing current would be V3 minus V1 over R1, okay? And that has to sum to 0, okay? Again, you know from looking at the circuit, there's 3 outgoing currents relative to that node. So you should have 3 components there, okay? So what's interesting to know from this approach, so with NVA, node voltage analysis, we did not need to find Vx and Vy explicitly. It was not necessary because we can get all the voltages that we need by using the difference of node voltages, okay? So the next couple examples are just going to be involving making sure we can write the equations. Typically, for the problems that we're going to involve, you'll get 3 equations and 3 node voltages, and then just using linear algebra techniques, calculators, MATLAB, whatever that's available to be able to solve those linear systems. So you are applying the linear system solvers that you learned from linear algebra class. But we're not going to go much higher than a 3 by 3. In some cases, maybe 2 by 2, but no higher than a 3 by 3. So let's go on to the example starting on the page of 48 and moves on to 49. Let's see if we can use node voltages and write equations. We're going to write KCL equations. So KCL is representing summing of currents, but we use node voltages to represent those currents, okay? So we'll go to page 49 now, and we have this particular circuit. Again, recognizing the lack of series and parallelism here. Again, if you look at this very carefully, R1, R2, and R1, 3, and 5 are not in parallel because of those two resistances there. They're not in series either because of this, right? Okay. And R1 and R2 are not in series either because you have this, off ramp here in the circuit there. And again, it must be end to end, no other options, okay? So we recognize we have 3 nodes and they've already been marked here, okay? So what we're gonna do is KCL at each one of the nodes. So we'll say KCL at node 1, then we're gonna do KCL at node 2. And again, we will do KCL at node 3. And again, we are specifically using node voltages. There is no need now to represent, a specific variable for the voltages across the circuit elements. Not interested in doing that because I can derive them if I have the voltage at V1, V2, and V3, okay? So let's do the currents. The outgoing currents for voltage 1, you have 3, okay? One of them, node voltage, notice where the ground is. So one of the directions is down from V1 to the ground. So using Ohm's law, that voltage differential would be V1 minus 0 or V1 over R1, okay? So it's very simple. When you go to ground, you could say minus 0, but it's not necessary. Just say V1 over R1. Then you need to go from node 1 to node 2, the difference in those voltages. So that would be V1 minus V2, and you passed through that resistance, okay? And then finally, you do have this outgoing current, which is coming from a current source there. And it is in the right direction. It's outgoing here. So because it is outgoing, we'll just say plus IS equals 0. Now, if this independent current source direction arrow had been the other way, going from left to right, it's coming into the node voltage. So we are always representing, remember, outgoing currents. So just keep that in mind. When we're doing these NVA problems, we're representing outgoing currents, okay? Let's do node 2. 3 possibilities here on current representations because you have 3 currents coming out. Let's go from V2 to V1. Going to the left, you pass through R2. So you'll have V2 minus V1 over R2. So when you're at that node, it's always the first subscript should be the node you're working at, okay? Then you can go from this current representation is from node 2 to the ground. So that'll be V2 minus 0 or just V2 over R3 because you'll go through that resistance. And then finally, you're going from V2 to V3 through R4. So V2 minus V3 over R4, and that sums to 0, okay? And then finally, let's look at node 3 over here. Again, 3 possibilities. Let's start at the node and go down to the ground. So that would be V3 minus 0 divided by R5. Then let's go from node 3 to node 2 to represent the flow through that resistance. So that will be plus V3 minus V2 over R4. And then finally, again, we're representing an outgoing current. So in this case, that independent current source is coming in, so we'd have minus IS equals 0. Or you could just put the IS onto the right-hand side, either way. Again, always represent outgoing currents, and that's it. And so what would happen is that we would need this value, that current source would be provided, and you would have a system now of 3 equations and 3 unknowns, and there's different ways of solving it. In this case, there's only you could solve for V1 in terms of V2 and plug it into these equations and get it into a 2x2 system. But using MATLAB, or any calculator-based solver for linear systems, you just need to be able to reduce it so that you can see the coefficients clearly, because the unknowns are the node voltages, and we're going to do that in just a second. Let's do one more example, and then we'll stop and then pick up next time, continuing on. So one more example here. Let's do example 2. KCL, get the current equations at each node. And that's interesting here. What's interesting here is, not so, we've seen this before, here's node 1, 2, is to notice this is all the same node. Be very careful. Okay, so you have a lot of currents there that, for that node. Everything there is all one node, even though you have 2 dots there, okay? So we'll push this to the top of the page, and then you flip over to 50, page 50 to do those, all right? So, and maybe what I'll do is I'm going to keep it on this page just so that we can see the circuit instead of flipping over. And what I'm going to do is write KCL at all 3 nodes, okay? And just leave it here. So we'll do KCL. Let's start off with KCL at node 1, okay? All right, so node 1 is over here, okay? And we're representing outgoing currents, remember? But we have an incoming independent current source. So we're going to start right off the bat with the fact that if it's outgoing, we'll have minus IA, okay? Then we will have the current flowing from V1 to V2, right? Or the representative voltage going from V1 to 2 is the difference divided by the resistance. So we should have what? Plus V1 minus V2, that difference divided by R2, okay? And then finally, we can go from V1 to V3 through R1. So we'll have plus V1 minus V3 over R1, okay? And sum that equal to 0, okay? Another way to look at this is we could pull the IA to the right-hand side, and what we're saying is that the 2 outgoings have to equal the incoming. That's KCL logic too, right? So you can represent the summing the outgoings, or you can still play the game of this is incoming, and we're using node voltages to represent outgoing. So use the node voltages to represent outgoing currents. But either way, that's the correct equation, okay? Then we can do KCL at node 2. Node 2 is right in the middle. Let's see, can you do that one? Let's go down first. So you would have node voltage 2 minus the voltage at the ground is 0 divided by R3. Let's go to the left. V2 minus V1 goes over the R2 resistance, and then go to the right. Plus V2 minus V3 over R4. So that one's pretty straightforward, equals 0, okay? And then finally, KCL at node 3. Okay? Being careful here. How many components are we going to have? Well, there's going to be a current coming to the top, to the left, down through this resistance, and then over to the right. So you have a total of 4 components this time, right? Let's start off with going up. So if you went up from this node, you would pass through R1 back over to this node voltage. So we have V3 minus V1 over R1. That's the first component. Then you could go from this node to node over through R4 to node 2. So we'd have plus V3 minus V2 R over 4. You could also go through that resistance R5. So it would be the voltage at node 3, which is V3, minus 0 at the voltage, which is the voltage at the ground. So you have plus V3 over R5. But then finally, you have another outgoing voltage here, right? Excuse me, outgoing current called IB. So we would add plus IB. It splits out that way as well, okay? It's an independent current source, okay? So again, 3 equations, 3 unknowns. The unknowns are all the node voltages, right? So we're going to stop there, and in the next lecture, we'll set up the linear system that looks more like how you would solve a problem in, say, your linear algebra class. But we now know how to use node voltages, all right, to find the particular voltages at any circuit element using their differentials. In other words, the difference between the node voltages. And by that way, we're getting representations for the currents as well.